And now I'll come to part 9 of class. And part 9 is about variational methods to 3D reconstruction from multiple views. So this is in one chapter, and what it focuses on is a lot of what we've seen now with the direct methods, also with bundle adjustment. These are sparse reconstructions. Reconstructions where you estimate a set of points in 3D. But as we know, the world is a dense world, and typically we want to infer the 3D world densely. And we've already seen one variational method in the last chapter, this work of Stümer et al. Here's the general idea of variational methods that are being deployed for dense reconstruction. And so why are these methods called variational? Well, typically you want to find a solution, let's say a reconstruction of your world, for example, by a surface that represents your object, right? So you want to estimate a surface in 3D, let's call it S, that captures whatever is in front of the camera. And that is my surface S, and how do I solve this problem? I set up an energy or a loss function on the space of all conceivable surfaces. This is something a little bit, maybe initially hard to grasp, so you have to consider the space of all conceivable surfaces in 3D. And each of them is associated with an energy or a cost. And then the idea of variational methods is that you minimize this cost with respect to the surface S. So it's an energy or loss minimization. Why is it called variational? Because the way you minimize these losses is if this is your space of surfaces, and here is your energy E of S, let's say like so, then you start with an initial surface, S init, initial surface that has some cost up here, and then you vary that surface infinitesimally to make sure the energy decreases. And then you basically go down the hill by, the gradient descent, for example, and that way you compute an optimal surface. And we've talked about gradient descent in the chapter on numerical methods and on bundle adjustment. So this is a baseline optimization algorithm. What's different about this here is that this space of surfaces is infinite dimensional. Right? So that's the difference. It's not a 1D optimization, a scalar parameter, but I estimate, so I don't update a single value here, but what I'm updating when I vary this is a whole surface. And so the way and why is it infinite dimensional? Maybe to give that a better intuition, if you take this surface and you perturb it in the normal direction at all these points, then each of these points is a degree of freedom to your optimization problem. And since it's a continuous surface, there are infinitely many points along that surface, and these are your degrees of freedom. And so mathematically speaking, you would call this an infinite dimensional optimization problem. And so it's a gradient descent, not in 1, not in 2, not in 3 dimensions, but in infinitely many dimensions. And so there are numerical methods to solve these kinds of energy minimization problems of this form. But the key is that this function u that I'm looking for is a mapping from R2 to R, for example here, if it's an image, or if it's a surface, it's a continuous object in R3. And in fact, that brings us one of the key questions here when you want to tackle 3D reconstruction as a variational problem. The first question is, how can I represent my surface S? What are good mathematical representations? And once you choose a representation, then this whole field is called shape optimization, because you have a shape and you want to optimize that shape to match your images. Shape optimization is a very big field in mathematics, and it plays a role in many areas. 3D reconstruction is one area where it plays a role, but also if you want to design airplane wings, for example. That's a shape optimization problem, right? You have material, steel, for example. How do you distribute that steel on your wing to get it optimal properties in terms of weight, in terms of stability, in terms of getting a good lift, etc., right? And aerodynamics. And this, you can imagine, designing an airplane wing or a car surface is a very complicated shape optimization problem. And whereas, originally people did that manually and tried different wings and looked what happened, you remember, it took centuries to develop airplanes. It wasn't easy, right, to come up. And often people looked at biology and said, let's look at the bird wings and see what they look like. And then they found, oh, they're slightly curved above. Maybe we should do the same, right? And so humans tried for centuries to make airplanes. It wasn't easy, right? And so this is still an active research area as well, to design car surfaces or airplane surfaces that have optimal properties. And these properties are multiple, right? You want them to not break, obviously, and you want them to fly and with, most efficiently if possible, right? So this is all challenges of shape optimization, and typically this is where the physicists come in and they tell you what the energy is that I want to minimize over the space of surfaces. And that energy should capture things like the wings should be stable, the wings should be aerodynamic, so you have ways to, for a given surface, to measure its aerodynamics, and then you bring that in here to make sure that whatever surface you come up with fulfills the requirements. And so this is a modeling challenge to put all of the things that you care about in your energy, and then come the mathematicians that deal with numerics of optimization. Once you have this loss function, how do you minimize it? That's a whole nother story. Right, so it takes a lot of experience on all these fronts to do shape optimization. And that's not just airplane wings, but any kind of materials, right, that you design, whether it's bicycles, you name it, right? And so you think all of these problems are solved up until someone comes out with a new bicycle and it's better than the previous ones, right? And so these are optimizations that are taking place. Now when it comes to shape optimization, there are different representations and they have different properties. For example, one property that you can look at is how compact are they? How well can I express that shape, and how much memory do I need? How much to store that shape with a certain representation? And then another question is, how efficiently can I compute the optimal shape? And that depends on what representation you choose, whether this minimization problem is feasible or not, whether it's computationally solvable, right? And unfortunately, the bad news is there is not one shape representation that has all the advantages. There are some representations that have some advantages, others have other advantages, and there is no one optimal solution, at least from what I know. By and large, there's lots of different ways to represent surfaces in 3D or shapes. By the way, they can be in 3D, but you can also consider surfaces in 4D, right? For example, if you model the deformation of an object over time, this can be seen as a surface in 4 dimensions in space and time, right? So for example, in 2D, all I need to know is this voxel inside the surface or outside, and is this voxel inside the surface or outside? But if you take a temporal surface, you can consider voxels and a timestamp, and you can say, is this voxel at time t inside the surface or outside? And then you have a 4D surface to represent an evolving surface. But that's also a shape optimization problem. There are 2 types, you can group all the representations that people have come up with into what's called explicit and what's called implicit representations. Explicit representations are often more intuitive. What you represent is, for a given surface, you represent all the points on the surface. Is this point on the surface? Basically, you store all the points that make up the surface of your object. And then you get something that is either a mesh or a spline surface or something like that. So there are different ways, and this is called an explicit representation. So you encode the surface points directly. And then you have, on the other hand, implicit representations. That means you don't store the surface points, but you basically label the ambient space. So for example, I will say, this is my ambient space in which the surface lives, and I will basically label all these points that I, shade here. I'll label these points as inside and the others as outside, and that way I have implicitly encoded the surface. That's why this is called an implicit representation. Here's an explicit representation. Typically you will have a polygon or something, but if you want a smooth surface, then there are so-called spline surfaces, which is in a way a generalization of polygons actually. And so the spline surface, it can be encoded with what's called control points, CI, and the basis functions. The basis functions are typically specified, fixed. You can choose a basis. And these are, for example, so-called quadratic basis functions, because they're locally parabolas, right? So this is a parabola opening to the top, and this is a parabola opening to the bottom. And so you basically concatenate parabolas to get this basis, these bumps here, these smooth bumps. And then you say, my curve, this is in one dimension, let's say, my curve is given by the basis functions multiplied with these coefficients that are called control points. And it's exactly like what you see here. This curve is encoded by these set of control points. And if I move one control point, if I wiggle it, the curve in that vicinity gets affected. And that is, for example, if the control point affects the basis function b2, it means in that parameter interval where b2 is non-zero, that's where it acts. So typically the area between these adjacent points here. In this part, it will move the curve around. So you can imagine if I wiggle one point, the corresponding surface moves up and down. What's really nice about splines, I've worked with splines a lot and I really like them, is it's an extremely compact representation. So what you see here, this entire curve is encoded by about 10 points that have 2 coordinates. So it's 20 double variables. That's all you need to encode this whole continuous curve. And you can move it around by, once you change these control points, locations, then you move the whole surface around. And if you want higher resolution, you can just increase the number of control points. But it remains a very compact representation of, and that's typical for explicit representations. Obviously, this is for curves, right? But you can do the same for surfaces, in which case you have control points, Cij, so it's a whole 2D grid of control points in R3. There they are. And then you multiply Cij with Bi of S, Bj of T, and then you have a 2D parameter interval, right? So some parameter grid here, and then that creates, and then you have this mapping that maps 2 points on that 3D surface here, right? So every point on the grid is mapped to some point on this surface in R3. And that mapping is this what I call S, the surface. And so this is the parameter interval, this is the parameter S, little s and little t, and for any st I have a mapping that maps to this surface in R3. And this is what this mapping looks like. And so here again you have that surface that you see here in purple, and then the little red control points, and you can imagine if I move them a little bit, then the surface that the area in the vicinity will move along accordingly. And so you can do shape optimization with splines. Rather than moving the whole surface, you move the control points that control the surface. Again, a very compact representation of shape. Typically, if you do it this way, and these are your basis functions, you would model open curves or open surfaces that have some boundary. But if you loop, you see here, we loop them around, so this basis function here, this one, it goes up here, Bn, and it comes back down here, right? So, and that way you basically close the circle, you identify 0 and 1, and that's how you get closed surfaces, just by looping the basis functions around. Now that's an explicit representation, spline curves, spline surfaces in R3, and that can be done in any dimension, right? I can have splines in arbitrary dimensions, doesn't matter. By the way, I mentioned shape optimization and I mentioned cars. That's where splines were invented in the first place. This was two French companies. One was Citroën and the other one, I forgot, but there's another French car company, and that's where the splines came up in the, I think, 50s or so. They wanted to optimize the surface of a car, and they did so by reverting to splines. They introduced splines to model car surfaces and optimize them. Renault and Citroën, these are the two French car companies that were extremely innovative in the, I don't know, 50s or so, or 40s, I don't remember when, long time ago. But you can read up, and it's quite a fascinating history of how splines came into the world. So it was on this topic of shape optimization for cars. Because until then, you know, it was very hard. You had a car shape. If you want to modify it, you know, how do you tell even someone what the shape of your car is, right? It's a smooth surface, and you know, you can send them the car and say, here it is, right? But if you want to represent it, let's say in a computer, you need to have some mathematical representation, and that's where the splines were invented. And obviously, if it's part of a sphere, that's easy. Anyone can represent a sphere, but you know, cars don't have spherical parts necessarily. They have smooth surfaces that you want to continuously modify and deform, and that's where you need splines. That's explicit representations, very compact, that's nice, but there is a very powerful alternative, and this is implicit representations. So representations where you represent the embedded, the ambient space. You label the ambient space in some form or other. And there are basically two popular ways to do this. Implicitly, one is the indicator functions. That's like super simple. I just label every point inside as 1 and every point outside as 0. Now if you ask me why 1 and 0, why not 0 and 1, doesn't matter. You can label the inside with 0 and the outside with 1. You know, some indicator representation that distinguishes inside from outside. And so by labeling every point in the surrounding volume as inside or outside, that's how I can encode any surface. And there already is a big advantage of implicit representations. I can encode surfaces that have holes, right? Let's say you want to represent a surface that has a hole inside, right? So like a donut. With a spline surface, that's not easy. Either you have a spherical spline or you have a torus spline, but you cannot go continuously from one to the other. It doesn't work. So in the case of camera-based reconstruction, I give you images of my object. I don't tell you what that object is. I don't tell you what its topology is. This is called topology. It refers to the number of holes of your object. Could be one hole, could be two holes, could be three, and it could change, right? If I put my arms here, that creates a hole here and a hole there, right? And if I move the arms, the holes disappear. So the topology of your object can vary from one moment to the next. With a spline, you can't do that. You specify the topology and it cannot just split and merge, right? With indicator representations like the binary labeling, it doesn't matter. You can label every voxel as inside or outside, and then you will have u equals 0 in here, u equals 0 in here, and u equals 1 in the donut, right? No problem. And in fact, this is one of the most powerful advantages when it comes to shape optimization of implicit representations. They can handle arbitrary topology and they can handle changing topology. Now, I said splines cannot. That's not quite true. You can engineer splines, and people have done that many, many times, that can split and merge. But it's a heck of an engineering challenge to make it work, right? It's not very beautiful. So a lot of, for example, if you have a curve and you want it to split, you have to basically check at any moment how close are the points of the curve. If they're too close, then I say, okay, make a split and create two curves out of one, right? You can do that, but you have to constantly monitor for intersections, and then whenever you have one, and at the critical point of meeting, it's ambiguous. Is it one curve? Is it two? Well, it hasn't fully split yet. So this is a lot of engineering to make something that works. I've seen amazing research and very wonderful techniques, but it's shaky, let's say. Whereas with implicit representations, you don't have that issue because you just label every point. Are you in or out, and you don't care what the topology is. The method is indifferent. There is another powerful implicit representation that I should mention. It's the so-called signed distance function. And so this is a function where you go a little bit further and you label the points not just as inside and outside, 1 and 0, but you actually store at each voxel a function that tells you how far is that point from the nearest surface point. So if I want to represent, say, a curve in an image, for this point, I will store what is the nearest point on the surface, let's say this one, and this is my distance to the surface, and that's what I assign to this voxel. And then if the point is outside the surface, again, I'm going to find the nearest point on the surface, and then I will take that distance, and by construction, I'll say minus d is the value that I store for points outside the surface. So I can distinguish inside and outside based on whether it's positive or negative, but I have more information. At each voxel, I can read off how far is not where, but how far is the nearest surface point. And that can be helpful. And this is called, if you just take the distance, it's called the distance function. And if you take it positive inside and negative outside, it's called the signed distance function, because you additionally have the sign that distinguishes inside from outside. So both of these representations are used quite frequently in shape optimization. A few words, I already started talking about it. The benefit of implicit so the drawbacks, let's say if we take the vantage point of the implicit representation, what are its strengths and weaknesses? The implicit representations, they typically need more memory, right? Rather than storing a dozen points on the surface, maybe 100, maybe 200, I have to label the entire ambient space. And so the memory, by default, the memory will grow for representing a curve. It will grow linear in the number of points on the curve, but it will typically grow quadratically for the implicit representations, because you have to label the whole ambient space. You have to basically specify the occupancy value for every voxel in space, and that, especially for 3D, if you want high resolution 3D reconstruction, that can be prohibitively large at some point. Now, all of these drawbacks and advantages, there are ways to fix them, right? For example, a very powerful technique to have efficient implicit representation is that you revert to what's called octrees. Octrees is, you may have heard of quadtrees for the plane, and octrees is the same in 3D. And it basically means you take your ambient volume and you group it into large voxels and small voxels, right? And here you say this whole big voxel is inside, so I label it as 1, done. And then when you're near the boundary, let's say here, then you make each large voxel smaller, and then you say, okay, this one is fully inside, and here I discretize again adaptively. And so you can imagine you take an adaptive grid that fine-tunes on where the surface is, and that's where you refine it. But in areas of space where there's only object or where there's only background, you don't need to refine the grid. And so you have this adaptive grid, and then you store the occupancy for that adaptive grid. And that way you have a grid that doesn't grow quadratically with your resolution, but that is essentially adaptive. And this is called octrees, and we've used that a lot for 3D reconstruction. Let me see if I can find a video of that in part 8. I think this may be a good way. So here you see an octree discretization in action. This was, I think, one of the, probably the first method that did Kinect-based dense reconstruction in real time on a laptop CPU even, on a tablet CPU. And one of the reasons how we got high resolution in real time is we used octrees. So you could see it in the beginning of the video, how we had this adaptive grid with coarse voxels here and finer voxels around the surface, right? And so we provide more discretization when we're near the surface to get a finer resolution, and less in areas that are all background anyway. And that way we can get fairly high resolution mapping in real time. So this was using octrees, for example. And so again, yes, they need more memory, but there's always solutions for this. The other thing is that moving or updating an implicit representation is typically slower, right? Rather than moving just a few control points here, like in the spline case, I have to update all the ambient space, the voxel occupancies, and that typically takes more compute effort. And so it's a little bit slower as well. But the implicit methods have massive advantages, which is why they're extremely popular for shape optimization. As I said, no, I didn't mention that, but what's nice about implicit representations is that they don't depend on a choice of parameterization. Let me explain what that means. It means if you have a spline or a polygon, right, then you have to label these points. This is point 1, this is point 2, this is point 3, this is point 4, etc., right? Now if I label the points differently and I call this one point 1 and this one point 2, and then that's going to be point 27, I have exactly the same shape. But you don't see it because the points, the vector of point coordinates is a different one. It's all permuted, right? And it's even more complicated. I could take an all different representation. I don't know, there's no other color here, where I take the points in between. I label this point and that point and that point in between the red points. It's the same shape, but it has a different representation. And that's not good. If you, in general, you know, in sciences, you want to find a representation for the things you care about, but it should be unique. You don't want a gazillion of different representations that really encode the exact same object. But with explicit parameterizations, you always have that. There is this reparameterization you can do. You can reparameterize the whole surface, and you get a completely different encoding of the exact same object. That is always bad. Why? Because let's say you reconstruct the object and then you want to see, is that an object I've already seen in my database? How do you compare two different objects, right? You cannot just compare the spline control point vector, because it will not be the same one possibly. Even though you're looking at exactly the same object, you don't see that it's the same object if you use this vector of control point coordinates, and then you might have two completely different vectors that encode the same object. So this is generally, it's much like the Euler angles and this, multiplicity that you have here. There, you don't want representations where the same thing has multiple representations. Why is that not the case for implicit? Well, in implicit representations, you give me the shape, then I'll tell you for every voxel whether it's inside or outside. There is only one way to do that. Either the voxel is inside or the voxel is outside. There is no ambiguity. So you will always get the exact same function u for the same shape. And if the function u is different, then it's not the same shape. Whereas with splines, if the spline vector is different, it might still be the same shape. And so this is a big issue, that there is a choice of parametrization that goes into explicit ones that I don't have in implicit ones. As I mentioned already, implicit ones you can represent objects of arbitrary topology, so the number of holes can be arbitrary. You can start with a sphere and you can end up with a donut or whatever else you want. Or you can have an object that is multiply connected. Maybe the shape that you care about has another component here and another component there, because maybe what you're looking at is not one person but three people, right? If you start with a spline surface, how do you want it to split to model 3? It's tricky. And the last thing that is not as obvious is that with implicit representations, and this is something we showed in quite a number of works, you can convexify the problem of optimizing shape. And this is not so obvious why that should be the case, but it is something that comes out in the mathematics. But to give you an intuition, if I start, let's say I want to reconstruct something that is a donut, right? But then I start with a surface that is around here, that is spherical, right? It might converge to this part, but it's not going to cover the interior somehow. And that's because it cannot jump. The curve, to get the optimal reconstruction, it would have to split and then somehow jump from here to there. Curves that evolve over time, they don't jump. They have to move continuously. If you do an indicator variable, it means you label every voxel. You say, is this inside or outside? And the algorithm will look at this voxel and say, is this in or out? And it can just label that voxel as outside, and thereby it can create material and remove material anywhere in space. And this is what you do when you update an indicator variable u. You basically, for every point in space, you can ask independently, should I put material here? Is this object? Or should I remove material because it's background? And it can do that. And that's ultimately why the optimization problem, when it represented with respect to implicit variables, often becomes convex. Convexity is a huge advantage because it means you can actually compute the optimal solution. And if your energy E is not convex because you have lots of local minima, then there is no way to compute the optimum. In 1D, of course, in 1D, even for non-convex problems, you can do a line search and find the best solution. Not so in infinite dimensions. Then it's hopeless. So minimizing a non-convex problem in infinite dimensions is not something you want to do. I say that, the whole neural network community is doing exactly that. They optimize very high dimensional problems that are not convex, and somehow it works, but as I mentioned before, no one really knows why. So let's look a little bit more into how can we do multi-view reconstruction as a shape optimization problem. So there's lots of different ways to tackle that, and people have come up with some of the most amazing ideas over the years. But one of the most powerful techniques is that notion of photoconsistency. I don't know if I have a drawing. Yeah. No, it's not a good drawing. So the idea is that, you know, we see that surface from two vantage points, say this one and that one, and then we say a point is likely on the surface if the color projected into each image is the same. So this notion of photoconsistency, we've had it before. So for this challenge, I should say we assume that the cameras are calibrated, meaning we know where each camera is located and how it's facing the world. So all we care about is not the camera, relative camera motions, but we only care about the shape of the object. And that means once we know where the cameras are, we can take points in 3D space and we can project them into cameras, different cameras, right? And then we can check for color consistency. And then we can assign to each point in 3D space a value that measures that photoconsistency. So that measures how well do the projections coincide in terms of their color. And I can do that for points on the surface, like here, but I can also do it for points outside or inside the surface. Maybe I should do a new drawing because this is getting a mess. So I'll do it here. So you have the surface here, and you project points on the surface or any voxel you project into pairs of images. You check, is the colors that I see consistent? And if the point is on the surface, you should expect the colors should coincide. If the point is inside the object, once I project, then I see this color here. And once I project into the other camera, I actually see that color there, and they're different colors typically. I would expect on average you should not see the same color. And same with points outside the surface. If I take this red voxel outside the surface, once I project into the camera, I actually see the color of this point here, and once I project into that camera, I see the color of this point here, right? So you see different colors. And only for points on the surface do you expect to see the same color. And so I can use that notion of photoconsistency to distinguish which points in 3D space are likely on the surface and which points are likely not on the surface. And by convention, I would assign low values of rho. I would assign values in some interval 0 to 1. And by convention, I would assign low values near 0 if the projected voxels give rise to the same color. So that should be for points on the surface. And high values near 1 if the projections don't match in terms of the color. And in practice, to really disambiguate better, you typically don't just check the color consistency, but you take a small patch around your projection and a small patch here, and you compute patch similarity, because that's more informative. Let's say if I take a wall like this one and I project points, then likely I will see the same reddish color because it's all kind of reddish, right? Or yellowish. But if I take a little patch, then I can start to distinguish whether it's really the same patch or a different one. And so this is how you measure photoconsistency, and you can do that for all voxels. And then here comes the key idea that was advocated by Faugeras and Keriven in '98. Then you say, find a surface that is maximally photoconsistent, meaning for all points of that surface, I want maximal photoconsistency. And how? Well, I take the surface S and I sum up the values of rho across the whole surface. So I aggregate for any given surface, let's take that one here, I aggregate the values of rho along that surface, and ideally I should get a small value if the surface is the right reconstruction. And I should get a high value of cost if the surface is not the right reconstruction. So that's very simple. The only caveat is now I need to compute a minimizer. And if you do this with a parametric surface, then you will invariably get stuck in local minima. Then you have a highly non-convex problem. And so, unfortunately, these loss functions are not convex as a function of the surface. And you can see why. It's because you move the surface around, and whenever you hit different values of photoconsistency, the energy will go up and down depending on what points you hit. Right? And so you cannot expect this to be a convex problem. More specifically, one can show that the minimizer, the global minimizer of this loss function is actually the empty set. And that's because the function rho, you saw it here, is always non-negative. So at best you will have 0, right? If you shrink a surface to nothing, then you have 0 cost, because you're summing up the rho values along all points of the surface. The fewer points you have, the smaller your cost. And this is called a shrinking bias, meaning this energy prefers smaller surfaces, and ultimately the empty set is the preferred reconstruction. And so you can see at a first glance it looks like the right approach, but then if you think about it some more, you realize there's something fishy with this loss function. In the sense that you would set up cameras, you would take images, you would calibrate, and then you run the algorithm and it would tell you there is nothing there, right? And you think, well, I see something, there is definitely an object there, don't tell me there's nothing. Well, this algorithm would tell you there's nothing. Not very clever in a way, right? Why was this not really discussed in the literature, say in this work? Well, people were not computing the global optimum anyway. They usually initialized in the vicinity of the correct reconstruction, somewhere here, let's say, right? And then they would move this to optimize photoconsistency, and that would give acceptable solutions. But I should say not really great solutions either. And so one question is, how can we prevent the empty set? And this is something we set out to do in this paper in 2011. We said, okay, let's take this loss function with the photoconsistency, but not now somehow enforce the information that there is an object, that I see an object. How do we do that? Well, basically, we have these observations. Let me do another drawing. So let's say here's my object, and then I have all these images that see this object, right? So I have my image plane here, and once I project this into my camera, then here is an area where I clearly can say there is object there, right? And for another image, again, I can also say, well, there is object here, right? So I know if I move from this voxel into 3D space, I have to hit the object somewhere. It cannot be empty, right? And so we wanted to enforce that. It's called silhouette consistency. That's the term in the community. It's called silhouette consistency. So you have the silhouette that you have in your image plane here, right? This is the area of the object that I see. And you should enforce that. And so what we said is minimize this photoconsistency weighted surface area, like everyone did, but such that the projection of the surface matches the silhouette that I see. So SI is that silhouette area, and pi of S is the projection of the surface onto the image plane. It looks really nice this way, because for all images I can constrain the surface. Whatever you reconstruct must match the silhouettes, and it's a hard constraint. There's no way around it. The key question is obviously in this way, how do you implement that numerically? And this is again a question of how do I represent my surface S. And as I argued, indicator functions are very powerful, so we chose an indicator representation. And then you can rewrite this optimization problem as you see here. And here I'll tell you why that is. So the first term, this is a very interesting term. If you have an indicator representation of the surface, so u is 1 inside and u is 0 outside, then the derivative of u, so this gradient is the derivative operator, gradient in x and y and z direction. This function will be 0 in most places because u is constant, and so the derivative is 0 outside. and the derivative is also 0 inside. The only points where it's non-zero is exactly at the boundary. And there the gradient is actually infinite because u jumps from 0 to 1 at the boundary. But it's infinite in a way that if I integrate the gradient, I get the surface area. So if you have an indicator representation of your surface S, then the surface area is nothing but the integral of this gradient d3x. So this integral gives you exactly the surface area. And more specifically, the weighted integral, so if I weight the gradient norm with the photoconsistency at that voxel x, and I integrate, this should be d3x to be exact, I dropped the 3 here. If you integrate this over the volume, you get exactly the photoconsistency weighted surface area that you have here. So this term is the same as this one. So that's really nice. By the way, this is a very popular expression in applied math. There's entire books dedicated to this thing. It's called the total variation. Total variation of the function. Variation. Some of you may have encountered that. If you do mathematics, you will likely hit the total variation at some point. It is one of the most well-studied and most powerful regularizers in applied math. And it has numerous really beautiful properties. One beautiful property is it corresponds to geometric properties like surface area or boundary area, boundary lengths, right? But another beautiful thing about it is it's convex. And that's very important because we want energies that are convex. And this is a convex energy. So what's nice about this energy is it is convex. Now, how do you enforce the silhouette constraint? That's actually also fairly straightforward on the indicator variables. I take rays that go out here, and let's say this ray is Rij. It's the ray for image I, so this is image I, and this is pixel j in this image, right? There's lots of pixels. And then I call this ray that goes through pixel j in image I call it Rij. And now if I have this ray, I can integrate the occupancy values of u along this ray. Basically count how many voxels are on if I move down this ray. Right? And now I can say if that pixel j is in the silhouette area, then I should hit at least one voxel. And that's exactly what this constraint reads. It says if I sum up all the occupancy values along this ray, then I should get at least one. Whereas if that pixel is not in the silhouette area, because it's a pixel outside here, then if I go along this ray, I will not hit the object ever. And so all the occupancy values should be 0, and hence that integral should actually be 0. And so that's the two kinds of constraints that we have. The silhouette constraint, I can boil it down to constraints on all these rays. There's a lot of rays and a lot of images with a lot of rays, but what's really nice is as constraints, these are linear constraints, because it's just a sum of u values being larger than 1 or a sum of u values being 0. And linear means convex. And so as a result, the loss function is convex, and these constraints, the silhouette constraints, are also convex, and that is ultimately why we can compute optimal solutions to these kinds of problems. And so here's the visualization. This is the silhouette Si in the image I. And here, if it's inside the silhouette, it will hit some voxel, at least one voxel will be on, and then the integral will be at least 1. And if it's outside, then it will be 0. And what we prove is that once you take, there is a binary constraint that the u's should take on values 0 and 1. That is not a convex constraint, but we can allow real values between 0 and 1, and then the optimization problem that we get is fully convex. And we show that in the paper, but it's not very profound. It's really because the total variation here is a convex cost, and these linear constraints are convex as well. And that means we can compute provably silhouette consistent reconstructions. And this is what I want to show you here with this approach. Here are 3 out of, I think, 33 images. The data set is online, and increasingly nowadays you can do 3D computer vision without a camera, because everything is on the internet. There's images, and that started already more than 10 years ago, that people like Yasu Furukawa put their data sets online and said, here's the data set. If you want to develop methods, try for yourself. And this is what he did. So he put the data set online, and these are the reconstructions that we were able to compute. And I know Yasu was very impressed by the results that we achieved. So here, for example, you see lots of fine scale details like the hammer or the sword are nicely preserved in the reconstruction. And in fact, these are preserved because of the silhouette constraint. Because when you just do a minimal surface approach with this photoconsistency weighted minimal surfaces, fine scale structures will disappear because of the shrinking bias. It prefers to just remove them, right? But if you enforce silhouette consistency, you get very nice reconstructions that are perfectly silhouette consistent. Here's more examples where you can see we can recover dense reconstructions from a set of images, typically 20, 30 images, and we can get very fine scale reconstructions where a lot of the creases in the clothing are properly reconstructed. And if there's one thing that I find a little bit puzzling, it's actually that now, almost 15 years later, the reconstruction quality of algorithms has not really improved massively. And if you take a set of images and want, an accurate surface reconstruction, I think these methods are still to date some of the most accurate ones. Maybe one more work in this line. You can also compute, you see the geometry is fairly accurate. Now what you can do is you can compute the color on the surface, right? This is just the surface itself. Once I see a surface in images, I can also try to estimate the color on the surface. The way you traditionally do that is very simple. You take the reconstruction that you have, you take your texture from the image and you just project it onto the surface. Very easy. Now the problem is there is no one image that sees the whole surface, right? So you need to project this texture from here and some texture from there and some texture from down there. But then what happens is the textures will not coincide. Right? In general, if you project this color from here and then some color from there, then this image will say, I see red, and this image will see, well, I see green. What do? They don't agree on what they see. In principle, they should agree, but in the real world, they don't, because nothing is perfect. The reconstruction isn't perfectly exact. The camera positions aren't perfectly exact. The world is not perfectly Lambertian, so the color may actually vary with viewpoint, right? And then what do? And then what you can do, and what is commonly done, is you average all the back projections. Yeah, someone is smiling already. That's not very clever to average. Why? Because it creates a blurring, especially if they don't agree. Then you get not red and not blue, but something in between, some orangey or whatever, right? And then you think, well, that's not really what any of the cameras saw. It's an average. And so what this averaging creates is a blurring of the texture. And you don't want blurring. You want sharp reconstructions with sharp textures, right? And so this is bad to average. Next you can do, and people have done that, so just to show you how sophisticated people got, right? They said, well, this camera is looking frontal parallel, so I'll give this camera more weight, and this is looking from an oblique angle, so I'll give that one less weight. And then they do a weighted averaging. Slightly better, it's a hacky solution, but yeah, that improves the texturing, but it's still blurry. And so what we set out to do, this is work from 2009, ICCV, is we computed what's called a super resolution texturing. And this is again a variational approach. It looks a little bit complicated at first glance, so let me walk you through this. What we do is essentially we do back projections of the texture onto the surface, but then we do it in a more clever way. Then we say, I have this image II, so this is my image, the brightness here, and what I see on the surface should match what I see in the image, but after blurring and downsampling. So what you have here is you have an operator B that models a blurring and downsampling. So pi I is the projection into the image. Pi I inverse is the inverse is going from the pixel back to the surface point, right? So this is pi I inverse of x, this point. And then I say the texture here, T is what I call the texture. Once I blur and downsample it, and this is done by this operator B, then it should match the observation. So I can actually model what a real camera does to an image. Namely, once you pixelize it, there is a blurring by the lens and a downsampling into pixels. And so what I expect to achieve by modeling it this way is I expect to achieve a very sharp texture that is high resolution and super sharp, and only after blurring and downsampling does it coincide with my observations. And so the aim is that I will invert that blurring and downsampling. Once I solve this optimization problem, I find the most sharp texture that after blurring and downsampling matches my observations. And then there is this total variation regularizer on T that we introduce with a very small weight lambda, because we don't want too smooth of a texture. What's really nice about this approach as well is this is convex in T. Why? Because ultimately this expression is quadratic in T. Even if there's some linear operator, it's still quadratic. And the total variation, as I mentioned, is convex, which means the whole thing is convex, which means I can actually compute the optimal texture. And we found an efficient algorithm. And so what you see here is the input, one of 36 input images of a bunny that I have in my office. And this is the textured reconstruction. And in fact, here is a comparison. On the left, you see one of the 36 input images. And as always with digital cameras, once you zoom in sufficiently, you see a pixelization in the image, right? And this on the right is the texture that our algorithm recovered. And as you can see, it's massively sharper than the input image. You see much more detail than you see in the raw input image. And since all images have the same resolution, they all have this pixelization. It's not like we have one sharp image that allows us to get the texture. No, from a lot of these pixelized images, we can recover one really high resolution texture. And so as a result, I hope I have a video of this bunny here. Do I have a video? No. I'll show you a video of the bunny. Let me pull that up. It's from a talk I gave last week at CVPR. Here is the reconstruction of the bunny, where we take a set of images and then this algorithm finds the optimal reconstruction. And you can see it's fairly detailed, but not super high detailed. And then we can compute the texturing, and this is the reconstructed bunny after texturing it. So it's super high resolution, and you cannot distinguish it from the original bunny by eye. And so this shows you where we're at, or where we were at 15 years ago with camera-based reconstruction, that we can recover objects at such a resolution that you can't distinguish them from the real object. All right, I think I'll leave it at that today, and we'll reconvene. I think tomorrow is a holiday, so we'll meet again next Wednesday. Thank you.